Good morning, everyone. We'd like to welcome you to our Human Systems Integration Knowledge Broadcast Series. And today we're lucky to have Dr. Rick Shearing as a presenter for Exploration Medical Capabilities. So just a brief overview, and to help you to understand how this discussion really is a topic that is rooted in HSI, we'll talk just very briefly about what is HSI. And I want to get off the stage quickly so that Dr. Shearing will have as much time as he needs for his presentation. So HSI is really a way to integrate human health and performance concerns. And it considers the crew as part of the system in the overall vehicle system or total system performance. That includes the vehicle, it includes the operational concept, and it's looking at the system, the crew as part of the system of systems, evaluating the crew needs. HSI also allows humans, meaning human health and performance, to be traded with other vehicle subsystems. And not just as an afterthought of after the vehicle's built and the mission is designed, but from the very, very beginning of the project, when you're first laying out the constructs of what the mission needs to do, and what the vehicle or vehicles need to do as part of the mission with humans involved, all the way through operation error and even through decommission. So human health and performance is really, it's really like the pieces of a puzzle. It's all linked together. And these areas are considered what we're considering here at JSC from a very top level, our domains or area of interest for HSI. And again, they all fit together like the pieces of a puzzle, and the puzzle makes the big picture that is human health and performance. And today we're going to be talking about space medicine, but really when you consider the human as a system, all of these puzzle pieces are truly integrated. So in other words, if you had to really draw the line between space medicine and what that means, or how it is provided, how it affects the crew on orbit and in preparation for the mission and after the mission, you'd have a hard time probably drawing the line between, well, how would you draw the line between that and habitability, or the environment that the crew lives in, or the countermeasures that they use before, during, and after to keep them fit for duty. Even personnel selection. All of these pieces of these puzzle are really, really tied together. So when you consider one, you really have to consider all to really look at the big picture and to do the right thing by the person. So today Rick's going to be talking about, again, this overarching sort of concept of operations, or how these medical capabilities are being viewed for constellation or for exploration. And the concept of operations is it's a look at the operational view or perspective of how the system that you're building, whether it's a vehicle, meaning a spacecraft, or a suite of hardware, or really the whole constellation program, which is a set of vehicles, a set of systems that work together. It's looking at the manner in which the user, the end user or users, are going to use that system in the environment that they're going to be in, or the environments. And so just like the cartoon states or shows, if you're building something without regard to what you're going to use it for in the end, or what the end users expect to use it for or need to use it for, then really the chances that your system is going to work and work properly are very small. And so again, just going back to the beginning of what we were saying, HSI is really connecting the dots. We all work in these areas where we are subject, many of us are subject matter areas for various aspects of these domains, but in order to really consider the big picture in regard to human health and performance, you really have to look at all of these together. So with that, I'd like to introduce Dr. Shearing, and have a couple of things here. I'm going to read off of this, so apologize about that. But Dr. Shearing started with Wiley as an advanced project physician, and back in 2006, he was the project manager for the Apollo Medical Operations Project. And during that project, they generated quite a few recommendations based on extensive interviews and coordination with the Apollo astronauts that affected or would affect and were intended to affect future exploration missions. And I've seen the pictures on this. He was also a co-investigator for the first lunar medical contingency simulation at the Houghton Mars crater at Devon Island. And so big learning experience there as far as looking at medical operations in a remote capacity. He was selected as a NASA medical officer in 2007, and he currently serves as the lead surgeon for Constellation Cross-Integration Program and Exploration Medical Capabilities. So with that, I'd like to introduce Dr. Shearing to give us a talk.
All right, thanks. All right, see some new faces. Oh, microphone, yeah. You know, I'm from Chicago. I talk really loud, so I don't know if you're going to really need it, but I guess the folks on the TV camera need that, so. All right. Let's get this all together here. How's that? Is that good? Okay. Well, for those of you who have seen me talk before, you know that it's kind of like riding a roller coaster, but I'm hoping to make this at least somewhat concise and that it'll adhere to how the HSI broadcast really works, because I actually really believe in what Deb and Kate are doing. I think the things I've learned over the last couple of years around here is the right hand's got to talk to the left hand, and I'm not a very smart guy, but I think I try to communicate well with other people, and I think that's the main thing from the lessons we've learned from the past, that the different side's got to do that. And we'll talk about some stuff, but this is going to be a lot of fun, I think. A lot of acknowledgments here. I'm really blessed to be a part of a great team, and really, if you think about it, we're in an awesome time in NASA's history right now, especially when we're the Apollo guys and thinking that we're, you know, on the verge of doing what they did, but at a much greater level, and the fact that we're part of this is really, really fantastic. Dave Bauman's our XMC project lead, helped me with a lot of the slides, and is just a great guy, and really provides a lot of the input and the work behind this. Kate and Debbie, I can't say anything about them. They put up with a lot for me because I've canceled on them numerous times, and they're very patient in trying to put this together. My partner in crime in Constellation is Jeff Jones. For those of you who know and love Jeff, he and I do a lot together, and whether it's good or bad, I'm not sure. Jen Fogarty is actually the new Constellation Cross-Integration lead, took over for me, and she's also been with me from Wiley from the very start. It's great. J.D. Polk's probably been one of my main mentors in space medicine here. He's the chief of space medicine now. I can't say enough about J.D. And then all these guys here are awesome, and I'm really privileged to work with them. Last but not least is my bride of 15 years. She's great and allows me to do a lot of fun stuff and takes care of our 5 kids. Does a wonderful job. So those are the acknowledgments. Okay, I threw this up here because this is the context by which we're going to do this. And I really, again, I embrace a lot of what Deb and Kate put together, that we're trying to educate personnel. So if nothing else, you're going to get out of this today, you know, what space medicine does and how we try to integrate everything. We're going to talk about some of the early stages of project life cycle and how this, what we're learning now and what we've learned from Apollo and those things, really will impact, hopefully, beneficially, the project as a whole. Talking about reducing costs and increasing safety and all that stuff, and hopefully in an effort not to do what these guys have done. I don't want to get on the moon or Mars and all of a sudden have something really catastrophic happen and then say, well, guys, just click your heels and maybe you'll get home. Maybe you won't. We don't know. You know, if we've done our work, and space medicine is really about preventive medicine. That's it. It sounds flashy, but it's really just prevention. If you do your diligence on the ground in terms of proper screening, training, testing your medical hardware, all these things, we don't have a lot of problems there. And for those of you who understand and know space medicine historically, we haven't had bad things happen in space for the most part related to medical problems. But in large part because we practice good preventive medicine, occupational medicine technique. So anyway, this is what we're trying to avoid, and I think the HSI broadcast, that's the whole point, is to make sure that the right hand's talking to the left hand, that everyone's kind of talking together, making sure that we've done this, so by the time it's showtime, we don't run into this, that we've considered all that. However, when you get in a situation like Apollo 13, it's because of all that prevention, that training, everything up front, that when something bad, off nominal happens like that, you're trained, you're ready, you can do it, and you know, you still have a good outcome. Okay, just going back historically, in tying with the HSI broadcast kind of objectives, you know, why is it important to know the history and what we've learned and stuff? And when I actually was asked by JD back in 2005, I just got back from a deployment with the Army, and he said, Rick, we're going to do this constellation thing, we're going back to the moon, and I want you to learn everything you can about Apollo. So spend the next however long you need, learn everything you can about Apollo, and then try to bring those guys back and ask them some questions. I'm like, wow, okay. I was 5 years old when those guys did their mission. That's kind of a daunting task. And one of the things that I came across that was very interesting, and there's a lot to talk about Apollo, but I just use it as an example of why what HSI is trying to do is important. I came across, I was looking at the metabolic expenditures, how much energy the crews were putting out on the lunar surface. And I noticed for all the lunar walkers, if you looked at their metabolic rate and their heart rate over the period of their EVA, they're expending most of their energy in the last 3 minutes of their EVA trying to ingress the vehicle. I thought, well, that's interesting. Why is that? Maybe they're deconditioned. Maybe they're just tired. You know, maybe they should be doing some exercise or something like that on the moon. So I went into this meeting with the Apollo guys asking that question. And when I asked them, they said, no, the hatch is too small. I'm like, what are you talking about? I said, well, the way the PLIS and the EVA suit was arranged, to get in the limb hatch, you actually had to contort your body, and it took a lot of energy to kind of fit through this thing. And this puppy, the display keyboard, which allowed you to punch in numbers to navigate to get back up the command module, was right above the hatch. And if you banged that thing and ruined it, you're stuck on the moon. So you couldn't do what you normally do in the hatch. You had to do weird things. And I'm like, wow, the hatch is too small. And I gave this brief to, I think, the SF group a while back, and Jerry Goodman was there. And Jerry's like, oh yeah, I was a part of that. Yeah, there he is, he's in the back. It's like, yeah, EVA changed, there's Jerry. EVA changed their requirements, and the hatch got, and in the end, the hatch ended up for 1.6U was too small, so the recommendation was just make sure that the guys are talking to each other so the hatch is the right size. Wow. Now, granted, they were healthy, they were, you know, they really didn't have any problems. And I posed the question to him, I said, well, what if you had an injured crew member, an incapacitated crew member, let's say you had a hole in the suit, you had to get in really fast, something like that. And their response was, well, death is a good motivator. So we would have gotten somehow. But getting back to the HSI broadcast idea about making sure we don't get into the situation, that's an avoidable problem. So anyway, that's kind of the spirit that I'm giving you this brief today. But we're going to tie in the space medicine side of it and try to tie in all these lessons learned here. So this is kind of the overview stuff. I really want to try to stick with this just to keep focus, because otherwise I'll go off on a lot of tangents and get everyone confused. This is kind of the main world that helps drive a lot of this stuff, at least from my perspective, on how we're going to accomplish all these things. So we take what we've learned from Shuttle, from Apollo, from Skylab, from ISS, and we get examples of things we need to start working on. And from my perspective, again, drives operational research. We want to develop an evidence base, and that's really important because we have, for those of you who have been working CEV, Altair, etc., the medical footprint for hardware is very small. So we really got to get this thing right. When I went back and looked at the kits and different things they had at Apollo, there was a lot of stuff that they had that they never used. And I was thinking, well, we don't really have that luxury with this. I mean, ounces are accounted for. Certainly they were for Apollo, but based on the fights we've had with engineering about where we're taking, everything has to be accounted for and used, and it needs to be based off a good evidence base. So we're developing that, and I'm going to give you examples of that. One of the main things we've been working in, and Eric Kurtzman and Sharmi Watkins over while I've been doing this, is the medical condition list. It's a list of things that we've either seen in space that models suggest it's likely to occur, or we've seen in analogs. Trying to put this together to make sure that, you know, here's the no-kidding list of things that we're probably going to see in space. After you've done your screening, after you've done your good preventive medicine practices, you're going to see this stuff most likely. This is what you need to make your kits to prepare for. This is what you need to train your crews for. This is what the surgeon on console needs to be able to treat. And that helps also drive our medical technology development, which is what David Bauman's shop is all about. But all that also helps drive our requirements. You know, what's the right oxygen concentration for the new vehicle going to be? What's going to allow the crews to optimize doing EVA frequently, but also not get into trouble with hyperoxia or hypoxia or hypobaria, things like that. We'll talk about that a little bit too. All kinds of things related to that. Also, the levels of care. Levels of care is not to be confused with standard of care. Okay, there's a big difference between the two. You know, the standard of care for treating, let's say, a laceration on the lunar surface should be the same way as Herman Memorial. However, the level of care when you think this would occur and how you're going to bring consumables and all the other things to treat that may be different depending on your mission. If you're just doing, you know, there back to the ISS, the likelihood of you developing a laceration is probably pretty small, whereas if you're on the moon for 6 months, it's greater, so you need to prepare differently, and that's where levels of care really guides us and helps us develop requirements. And then you get into the human system integration requirements that really define how you put a human in the loop, keep them safe, and all the things that they're going to need. The requirement integration takes all of this and gets the surgeons involved at every level, Orion, the Lunar Surface Systems, EVA, to make sure that we're taking the requirements, we're getting them integrated, making sure our SA's interests are being taken care of. Great example of how that's working is at 1 o'clock I go to the Constellation Flight Operations panel, the flight directors, and defend our crew scheduling restraints. The crew and the surgeons have worked together for months on trying to come up with what exactly is going to be the crew work day. Engineering's thinking, well, maybe they're getting a little bit too much time here and there. Well, we're going to say, on the benefit of the crew, on behalf of the crew, this is what they need, this is why they need it, and hopefully everyone's going to buy into this and see it the way it should be seen, at least from our perspective. So that gets into the requirement integration. The design, some of the funnest work we do is really helping build this stuff right now, and we should, along with our SF and SK colleagues, integrate and making sure that the suit's being designed for the human loop, because we're the experts on the human, right? So getting our input on this, and it hasn't always been that way. I'll tell you some stories about that later on with some of the projects, but it hasn't always been that way. Same thing with Altair, Orion, making sure that we are hands-on, all of us in SA, making sure that we are getting in there to make sure that the hatch isn't too small, or something else, that the waist ring that they were initially going to design into the launch landing suit isn't designed there because it's actually going to break your spine, things like that. May seem obvious to you, but I can tell you from experience, learning the lessons of the past, things that should have been seemed obvious weren't, and had impacts on crew's health and performance. Then verification. We take all this really fun, cool stuff and we test it in an environment as close as we can get to. For those of you who heard our Houghton Mars pitch from a couple of years ago, that was a great example where we took a concept, an idea, we went up to a remote place, tested this, learned a ton of stuff about that. We also had the opportunity at NEMO and other places to test our hardware, see what we're doing. So with that, hopefully we'll get back here and we'll have a flawless show. And generally, on our side, the life sciences side, if we've done our job up front, if we worked hard to do all these things, nobody really knows about us. That's the way it is. Certainly in space medicine, that's the way it is. If something goes wrong, either, we dropped the ball on something, or it's just, you're dealing with humans, which are certainly seem to be in the last of the priority list as far as the vehicle goes. Okay. So operations-wise, a lot of stuff. I just picked kind of a list of stuff that we've dealt with from an ops perspective that ties in with all the different things, research requirements, et cetera, et cetera. Right now, in-flight sleep disturbance is probably all aware of one of our big issues because crews need medication to sleep, and that impacts how they can react to caution and warning and all these other things. Some very interesting stories that have come out of that. So Smith Johnson, Lauren Leventon, the BHP group are doing a sleep study. I was actually a part of it. We actually spent a couple nights in the crew quarters. You take a placebo or a drug, and then they wake you in the middle of the night. You got to go to the computer, do vigilance task things, all these kind of things that the crews would have to do to try to actually figure out what is the right drug or combination of drugs the crews can take so that if they get a caution warning in the middle of the night and they're trying to get restful sleep, they can wake up and do what they need to do. Very, very important work. But that came out of ops. That came out of the crews saying, hey, I'm not getting restful sleep. I need to take this drug, but I take it. I can't wake up. That's not good. Postflight herniated disc, this is a very passionate area of mine because I've taken care of a number of the crew members who've blown disc post-flight. Smith Johnson, Mark Campbell, Alan Feiston, and I are just finishing a paper on this. We've had a statistically significant number of post-flight herniated disc in astronauts. One occurred on landing day. That's a problem. I don't want my crews, whether it's terrestrially, going to the moon or Mars, to get there and blow a disc. What can we do to prevent this problem? What's causing the problem? We don't really know. So this is leading to a research issue that's eventually going to lead to a requirement that'll lead to a design implication, et cetera, et cetera. That's actually what a L2-3 herniated disc looks like. One of the things you get to do as a flight student is actually go with your crew member in surgery with the neurosurgeon and actually get to the system on doing these procedures. So you see the continuum. You diagnose the astronaut with the problem, you follow them through, you do surgery with them, you follow them through rehab, and it's just a continuum. I was a family doc in private practice before I went back to live the dream. And that's the way family practice was. That's the way I practice, and it's a lot of fun to actually do it here too. Lunar dust. We got a great group called the LAD Tag. For those who are familiar with that, it's a lunar lunar airborne dust toxicity analysis group. And all we care about is dust. It's great. You go to a meeting with these folks and you talk about dirt for a couple of days. It's a lot of fun. But dirt was a huge issue. One of the main things we learned from Apollo is dirt has to be engineered out. We had a wide range of reactions to the dust, from mild upper respiratory irritation to frank coughing and other problems. So this is something, if we can engineer this out, it'll be great. Huge implications for us because really this medical, biological problems driving the architecture. The airlock is being driven really on Altair and Outpost, in large part in the design for the Lunar electric vehicle, because of Lunar Dust, trying to keep it out. So talk more about that, but that again is an operational problem. Thrust oscillations, that's another thing we've had a blast with out at Ames, taking the crew, putting them in either a centrifuge vibration table or just a vibration table, shaking them at different vibrations, and then find out what's their level of performance in which they can read a display and actually carry out a task. I actually got to do this myself, which is a lot of fun. You just sit there like that, and you try to answer questions and stuff, and it's tough. But we're getting real answers for what the crew's limit on launch stage 1 is going to be for carrying out these tasks, what the display, the font size, the color combinations are going to have to be. A blast. But that's, again, an operational question. It has huge implications to that vehicle for anybody who's been following that. That's another thing we got to get right, and it's a lot of fun. Risk factors for lunar surface injuries, again, a preventable problem. We asked Apollo a lot about, what are risk factors they considered for getting hurt on the surface? They said really relatively few. It's hard to get hurt on the surface. We'll talk more about that later. But again, an operational problem that drives research, that drives requirements, that requires developments, etc. In-flight hypothermia, for those of you who know a lot about Apollo 13, it got cold in there. The command module was about 39 degrees. The lunar module was about 44 degrees. Crews were hypothermic in addition to being dehydrated, sleep deprived, etc., etc. When we wrote the HSI requirements, we did not have any requirement for thermal protection. This goes back to the SRR back in 2005, and one of the requirements that Jim Lovell and Fred Hayes gave is make sure you pack a thermal blanket. One of those little light kind of aluminum things you get after you run a marathon. And I thought, well, for sure, we've got that. And I looked back, couldn't find it. So something like that, we didn't think of it, but in the event you have an electrical failure, I know Orion says we'll never have an electrical failure, but if we have an electrical failure, at least the crews can get protected somehow, and very little mass impacts, et cetera, et cetera. So, anyway, operational issue. EVA suit issues, a lot about EVA suit issues. That's driving a lot of the stuff that we do. They fell a lot, but again, it wasn't an issue about getting hurt. It was just efficiency and mobility and things like that. And then landing and recovery. Again, a huge issue. One thing we know for sure, despite all the other things that we talk about in Constellation about landing and recovery, is they're going to land, hopefully, if they hit the Earth. And they land in water. Well, again, we don't have a lot of recent experience with landing in water, so a lot of the issues that we think we're going to have to deal with, we went back to Apollo to learn about, but we're trying to figure out now to make sure we get the water recovery issues right. So anyway, operational lessons learned, and my favorite is waste management. If you've heard the Apollo brief, this was the bane of Apollo's existence, pooping in a Ziploc bag, not a lot of fun. We took that information, made sure Orion had a toilet, had all the things to make sure that the crew's functional needs were taken care of, including off-nominal output. So all these things were very important. Again, operational issues, driving research in some instances, not necessarily. This is kind of a no-brainer. Just have a toilet. Control odor. Adapt male and female anatomy. Kind of a no-brainer, but again, it's not that straightforward sometimes. Okay, just want to mention the injury prevention stuff, only because, again, this gets back to some of those important lessons learned. It was hard to get hurt on the lunar surface. I didn't necessarily believe it, but the week after we met with Apollo, I did a set of lunar parabolas on the Vomit Comet and tried hurting myself. It's kind of a flight surgeon Army guy thing to do. I push off on the fuselage, try to slam into the ground, they twist a wrist or something like that. You can't do it. It's exactly like the Apollo said. You have time to fall. It's kind of like, just like a little baby, you fall. However, if you're going in really steep slope terrain, if you got run over by your rover or something like that, or certainly fall from a height, you could get hurt. If you remember, the limb ladder was just shy of 6 feet. This puppy on Altair is going to be anywhere from 20 to 28 feet. Wow. Now your inertial mass isn't changing on the moon, even though it's 1.6 G. So there's potential with that suit and everything else. You could get injured. So there's things we got to think about. But in terms of busting hips, busting ankles, and stuff like that, yeah, the hazard's there, the risk is small, but I don't think I'm going to be training the crews to do external fixators in their hips or do ORIFs or anything like that, because again, the risk is low if you plan smart. We're going to tell the flight planners, don't plan operations along a steep crater unless you have some way to secure them, so in case they do trip and fall in this thing, they're not going to go tumbling down, especially in the permanently cratered or permanently shadowed zones, because they're about minus 40 Kelvin or something like that, Tom? Okay, what about water egress stuff? Again, operational issue, just give you some examples that you should take home. We didn't know much about water, but Serena Unnen, one of our Star City flights, was training with the ISS crews out in Star City, and they have to do a lot of water recovery training, and you know what? The videos aren't going to work. I knew it. Anyway, just showed us something that was very eye-opening to us who aren't Navy personnel, that water, it doesn't take much in the ocean to really be provocative. And one of the things we learned from Apollo is that you know, almost all the Apollo astronauts were naval aviators, with 2 or 3 exceptions, and they all got seasick pretty quickly after they got back. So this is all issues. When the requirement came out for a Constellation, they said, well, you know, you need to be able to build a vehicle, take your crews, and at least Beaufort Class 8Cs. Whoa, anyone know what a Beaufort Class 8C is? You're talking about Cs that are upwards of, what, 18, 20 feet? Now, they narrowed it down to what, a Beaufort Class 5, 12 to 14 foot Cs. Now, again, I'm an Army guy, I like the land. But I've been in 2 to 3 foot Cs. Doesn't take much to start getting going. Now you think about it, neurovestibular deconditioned crew member, et cetera, et cetera, et cetera. Big issue. So our input based on our operational experience helped at least try to get some sanity into these requirements. I don't know if we're successful with that or not. What do we expect to see? Again, this gets back to this condition list. And again, this condition list was important because it had to be based on stuff that we saw. But not only that, the collective experience of all the flight surgeons that we had around. So we did this Delphi. We got all the surgeons in the room for a day, sat around, asked them based on their mission experience, what have you seen, what have you not seen, what are you concerned about, what are you not concerned about, et cetera. Along with that, in-flight medical data collection. We've been doing a lot of that. We published a paper on in-flight muscular injuries and minor trauma this past February in the Aerospace Medical Journal. Eric Kurtzman and I and Lynn Saylor are just finishing a paper on in-flight back pain. A lot of data collection to find out exactly what the incidence of these conditions are of in-flight occurrences to drive what we're actually going to take, what we're going to need. Again, this is important because it drives our kit design, et cetera, et cetera. What conditions do we expect to see for long lunar stays? Well, this is the condition list that hopefully will come up. Can I open it? Dang it. There's a long list that Eric Kurtzman and Sharmia Watkins have developed based on the stuff that we know so far that scores the likelihood of a condition occurring, the impact to the mission, and how preventive medicine strategies mitigate that risk. Excellent evidence-based for us to start developing this because it gives us some forecast of what the outcomes might be if you have closed head injury, or if you have a laceration, or if you have diarrhea, or if you have things that we've actually or things that we've seen at least in spaceflight or an analog environment. That's actually the core modules, the kind of the cylindrical model. There's a lot of different models right now for the lunar outpost. What do we expect to have as far as what we're going to need for all this stuff? That's a very important thing. It impacts a lot of what we're going to do as far as our capabilities. Jeff and I, along with a lot of others, Tom was part of this paper that we were going to have published, or actually a book chapter this summer on interplanetary space travel, figured that from a medical standpoint, to take care of all the things based on that condition list, these are the things that we're going to need as far as lab analysis, urine, saliva, all sort of stuff. I also want to throw something in here about a paper that Mary and I and Mark Shavers and Marcelo Vasquez worked on. The question that we were asked about that ties in a lot of this integration stuff was, you know, would the crew members, if they're on a lunar surface in their suit, hopping around, sustain, if there's a solar particle event, would they get whacked and die in their suit? Well, when I got asked that question about a year ago, I'm like, I don't know the answer. I'll ask some smart people about it. And we actually put a team together and wrote a white paper, and based on modeling and all these other events, determined, no, you probably would not die in your suit. However, you could have other problems, predominantly radiation sickness and illnesses, a week out, and then you have to prepare for that. You have to have, your lab capabilities to follow your white counts, et cetera, et cetera. But again, that was something that hadn't been done before. The team just got together, the best minds in their different areas, and came up with what we feel is a pretty good evidence base for planning for something that's really got a lot of people spooked as far as lunar surface operations. I think we have a pretty good handle on that. There's probably more work, research that has to be done to validate that, but that's a good example of how, again, we integrated across the disciplines to make sure that we're coming up with operational answers. Something else in regards to that herniated disc stuff, we just pulled together a panel of 12 neurosurgeons, spine surgeons last week to get their input on this herniated disc problem. We got the best minds in the country to get input on this and how we could actually do in-flight studies of the intervertebral disc to see what actually happens to the disc. So we're involving SK, the research side. We're getting engineering involved. This is actually a collaboration with an ND PhD student at Harvard MIT who's developing a device to allow us to do this in flight, so we can actually get in-flight evidence for what actually is going on. Again, it involves a lot of disciplines, but certainly is going to give us answers in something that we've never had answers for before. The implication, I think, is really exciting for NASA is we really don't know what causes low back pain terrestrially. Okay, that's the second most common problem a doc sees in their office in primary care generally. we start getting a handle on what the pain generators are in back pain because of our work here at NASA. You can think about the implications and all the spin-offs that have benefited everyday people out there. You can't do studies like this in the real world because you're actually trying to induce a problem and then study it. You can't do that, it's called unethical. But in space, we know we have this problem. There's flying in space. It's not necessarily impacting the mission, but we can study the changes compared to pre and post. So I think, again, thinking long term, I think there's some real excitement there. How do we come up with the atmospheres for the vehicles? A couple of years ago, we were asked that question, and Johnny Conkin, Gernhardt, Jones, and I did a white paper on exactly what would be the most optimal Constellation atmospheres. So we took an operational consideration. You know, Apollo was 100% oxygen at 5 psi. Can't do that because of flammability issues and stuff. But certainly we want to maximize the environment for EVA, et cetera, et cetera. So what was the best environment? And we actually went through, did a pretty thorough analysis, and came up with this relatively hypobaric, hypoxic environment that allows the crews to be able to actually only have about a 30-minute pre-breathe to get in and out to do EVA in the lunar surface, but it also minimizes their risk for DCS. The risk for acute mountain sickness is there, but the sea level equivalent is anywhere from 65 to 7,500 feet. You generally don't see acute mountain sickness at those altitudes, but certainly would drive how we would design our kits. Maybe you want to carry a little Diamox, maybe you'll carry a little bit of anti-inflammatories or steroids, but again, likelihood is low. But again, an operational question drove research that drove a requirement that's now going to implement how the vehicle is actually going to be built. Pretty exciting stuff. How about medical technology and development? Again, really great stuff here. You know, we use ultrasound right now, but David's actually been working with a couple of the universities on high-intensity focused ultrasound, where you actually use ultrasound, which already exists, but actually you can modify it and manipulate to actually be therapeutic. So you can actually cauterize bleeding tissue, you can blast apart the kidney stones, et cetera. So you have an existing technology, but again, it's something that we might be able to modify for spaceflight, but also you could have spin-off again for everyday research. Non-invasive blood analyzers, that's real exciting. We know we're going to have be able to have the capacity to do blood analysis. However, having blood, reagents, all that stuff is a mess. We're trying to develop a way you can use mass spec or some type of technology to be able to measure your sodium, your electrolytes, your sugar, et cetera, et cetera. Again, something else that has amazing benefits. Again, you think about the potential of the 47 million diabetics in this country being able to just put a little probe on their finger and get their blood sugar as opposed to doing blood sticks every day. Incredible. Again, a massive spin-off. We're very excited about it. The lightweight trauma module. This is basically a closed-loop ventilator system, smart technology. Tom Hadfield worked on, I think, really spearheaded a lot of this collaboration with the military. I mean, this is an 18-pound device, I think. This thing is a closed-loop ventilator, 18 pounds, and along with an oxygen concentrators, can deliver tremendous capability for someone who might need to be intubated on a respirator. Now, you have to ask yourself, Doc, if you're doing all this great preventive medicine, why would someone have to be intubated, and why would they have to be on this device? Well, that's up for debate, but you cannot remove the risk for toxic inhalation. Again, we don't know if you got a huge dust burn, you got acute silicosis or something like that. If you develop a chemical pneumonitis and have respiratory distress, you might need to be in this. The issues are there, but certainly that would be a showstopper for the crew or the mission. I think this capability is sound. Real-time radiation dosimetry is something that we learned from the Haunt Mars project. We don't have that capability. We need that capability to be able to measure at the tissue level what's going on and then be able to report it to the surgeon and Schrag on console. This is a kind of neat device my colleagues at USERO, where I'm stationed in the Army, it's a ultrasound stethoscope. You know, we've had a lot of problems with using stethoscope, even digital stethoscope on orbit because of the background noise. This actually uses ultrasound. Very neat device. The Army has a real interest in it because when I'm in the back of a Black Hawk with a litter with a patient, you can't hear what's going on. You cannot auscultate the heart, you can't auscultate the lungs or anything like that. Not different from ISS or certainly the vehicles we'll be dealing with, but you can use ultrasound. Now, there's a big learning curve there because there's differences in the way the normal heart sounds, lung sounds are being transmitted through ultrasonography, but I think it's a very sound device. The Army is very interested in that because of their operational needs, and I think may have a place with us. Okay, so, we doing okay? I'm talking fast, but okay. So where does this go as far as requirements development? Well, this is the main one. This is our level 1, or I don't want to confuse things. This is kind of the top level requirement that guides everything in human systems, and in it is levels of care performance standards. From that, we get the HSIR, which is our level 2 kind of requirements, and from there we get our vehicle requirements and specs, level 3, level 4, level 5 requirements. So, going back to levels of care, this is where we're defining level care 1, 2, 3, 4, 5 based on the mission. And for our interests, for lunar missions, we're talking about boots on, or a round trip, 7-day boots on the ground and return, less than 30 days. That should be 30 days, and then greater than 30 days. Again, the technology seems pretty robust, but relatively speaking, it's certainly not like an intensive care unit or an emergency room or anything like that. It's really akin to what you might have at Everest Base Camp or something like that. So limited capabilities, but we'll have very, very well thought out plan for how we're actually going to conduct that. Who's going to conduct the medical care? Again, there's no requirement to have a physician for long lunar stays. It would make sense. Certainly for Mars it would make a lot of sense. But right now, you know, our crews get 40 hours medical training. That's it. You know, they start off with, you know, classes, and we say this is Mr. Stethoscope, and at the end of 40 hours they're conducting a mega code. Not a lot of capability, but again, that ties into the care provider, et cetera, et cetera. But levels of care really guides the requirements and how they're going to be developed. And these are some examples of medical requirements that come out of the whole levels of care. Lunar dust contamination, measurement of physiological parameters. This is an important one because prior to us taking a real good look at this, the lunar suit would have had EKG monitoring. And for those of you who've been around for a while, you know that, well, shoot, we always monitor the heart rhythm in crew members. Well, that was an important question because that had very important implications for the suit design for the launch landing suit, the lunar suit, in addition to what you would do with the information. If the information fails as you're going out the door, do you still let them go out the door? What are the current practices right now in the flight rules for ISS and shuttle? Anyway, long story short, we got the best minds in cardiology really in the world, got them here, told them what our issues were, and in the end they said, you know what, you guys really don't need to have this. And we deleted the requirement for a lunar ECG in the suit. Wow, that's huge. Again, we did it based off an evidence base. It has huge implications for the program, but again, we went back and looked at this. Now, I'm a doc. I like information. I would love to have had heart rhythm, all kinds of stuff, but again, operationally speaking, what am I going to do with the information? What if it fails, you know, along those lines? And you just have to wear that kind of hat. So that was very important. Exercise capability, near and dear to my heart because I love to exercise. Problem with this is exercise is not deemed by everybody to be important, and the word from the moon was lunar surface EVA was enough exercise. Well, we had limited data, but the data we had suggested that from a cardiovascular, from a bone and muscle standpoint, really it wasn't, and we really need to have exercise capability. So we have a requirement for that. Potable water for on-orbit drinking. For those of you who've been around, you know the battles we've fought to make sure that crew members get enough water. We finally won it, but this went back and forth, back and forth, back and forth with the program. They wanted to know if we withhold water, because they wanted to withhold water because they felt that the crews historically didn't need as much as we were asking for, what bad things would happen. And we had to inform them, in medicine you can't do studies where you intentionally withhold bad things from people to see what, or withhold good things from people to see what bad things happen. Again, it gets back to your best clinical judgment and experience. So, you know, David gave me this slide to show how requirements integration is done, and I know engineers love this kind of stuff. You know, the flight surgeon kind of is interacting here, there's Pete and stuff like that. But it doesn't do a lot for me. We're involved. We kind of just do stuff. We hang out, you know. We got some issues associated with, you know, different hardware or whatever. We'll go out there and scuba dive and hang out. That's Pete Bauer, Keith Brand, Bill Tarver, and me. You know, we just try to do this stuff in the environment we think we're going to be in, and we have fun while we're doing it. And that's a lot of fun. So as far as design, so we're moving into design. We've got the requirements, we've got the questions, we needed to interact with design. One area that I thought I'd bring up here was thrust oscillation. For those of you, it's not going to work. Shucks. This is the Ames centrifuge, and we went out there last fall, and Marcia said I could use the videos, clips that you're not unfortunately going to be able to see. We put folks in a centrifuge on this table. We spun them at 3.8 G in the GX. We vibrated them up to 0.7 G in the GRMS. So they're getting shaken in that, asking to read displays, and you'd see how vigorous that vibration with Marcia, both in the lateral and the AP view. And I did this test myself, very sporty test to be actually be able to do this. And again, it's helping us understand exactly how that vehicle is going to be designed. This is another thing that's been very interesting. It's an ongoing study right now, but the first part of this study we did looking at the ESR2 config 1 suit, the launch landing suit. Remember, way back when the thought was, you know, the program was going to give us one suit for launch landing and lunar surface operations. One thing that we learned from the Apollo Medical Operations Project was you got to have a waist ring. They didn't have one in the A7LB suit. They couldn't bend forward. You got to have one in there. Well, what's a waist ring going to do to your spine on launch or landing? Certainly landing and impact. Now, everyone in this room probably say, well, it's probably going to hurt you. But we didn't really know if it would be tolerable injury or something that was catastrophic. So we actually did some studies using fresh cadavers We used the cadavers. We put in accelerometers in all the different sites and used this pneumatic arm with the waist ring to impact the body. Then I did the autopsy afterward, and then we did these 3D reconstructions with CT scan and found that you would have really nice L1 transverse body fractures, vertebral fractures. Actually, when I dissected out the vertebral column, you see these big fractures in there. Went back to the program and said, okay, we thought it was a bad idea, here's the proof, bad idea, knocked out the waist ring. Okay, we got the evidence. No study like that had been done before. You may remember the Chronicle ran an article, a couple months ago, and Dustin Gomer, who was one of the project leads for this, you know, we were getting castigated by some people about doing this kind of research. You know, NASA is unethical, they shouldn't be doing this kind of research. And Dustin very pointedly came back and said, you know what, if we're using humans, we should be using humans to test the stuff that we think we're going to be doing to get the answers that we need. And actually, in the end, was vindicated by the fact and the way that the Chronicle wrote the articles that NASA's doing research that they should be doing. This is the right thing to be doing, this kind of stuff here. So it was really, really nice to actually get some backing in this. Anyway, that was a lot of fun. We're doing those studies right now, looking at the new designs for the launch landing suits, looking at how the shoulder side bearings, the upper arm disconnects, and the thigh disconnects would impact a crew member at nominal and off nominal, one parachute out landings. As far as vehicle development goes, I don't have a lot of pictures about Orion, but right now I've been involved with doing the Altair mock-up evaluations. You spend a couple hours in there figuring out exactly the human factors issues. Robert Howard and his team runs this. That's a blast. They're doing some really, really important work, asking us, you know, what it's like to actually, you know, conduct operations, do tasks and things like that, just to get an SF or a human factors perspective on this. And then this information goes back and impacts how the vehicle is actually designed. I can tell you, you know, we set up these bunks in there. We all slept in there. We did these things. It's a pretty funky environment. You're talking about anywhere from 1.8 to, I think, 2.85 meter diameter vehicle. I think they finally chose, what, 2.25 or 2.35 meter diameter for Altair. Still working on it. But I'll tell you, 4 people, 7 days in this thing, you're pooping next to each other, you're eating next to each other. Just like Apollo said, it's going to be, it'll be very interesting. But this, again, kind of work you got to be doing. We're involved with the design, telling people, okay, you know, during this sim, I threw in crew member got lacerated. How we're going to actually sew up this laceration with the guy bleeding all over the place, find the kits. It turned out it was a very difficult thing to do something from a medical standpoint. It's actually fairly simple to do, just sew up a laceration. But all the stuff you had to go through to get everything right so you could sew the guy together was something that we need to do. This is the environment to do it. Robert and the SF group, Tom, are doing outstanding work with these different mock-ups. We give input on how we should design the different scenarios for outposts. I think there's 12 scenarios that Lunar Surface Systems looking at, the cylindrical design, the torus design, where, you know, would be the best place to put the medical hardware to carry out medical operations, stuff like this. Again, surgeon, SF, we're all being integrated to make sure that they're designing this thing right. And again, what are the things that we think we're going to have to treat in there is based on the evidence-based, the medical condition list, and all those other things. We're not doing pie in the sky kind of stuff. This is stuff that we think, no kidding, we're going to actually have to do. And it's important that that message is propounded from NASA, because you go to the internet, you go and see what other groups are doing. There's some wacky stuff out there. A couple of years ago when Steve and I did the Haunt Mars project, a project had been done up at Haunt Mars previously where this team was out in the, you know, out on the so-called Martian surface, and they came across an unconscious crew member. And I thought to myself, what? Why would you ever have an unaccounted for crew member who's just laying on the ground unconscious? Well, they ran this whole simulation based on this unconscious crew member. I'm like, what the heck was that about? You know, when we designed our sim, we went back to Apollo, asked what were credible scenarios where you'd have an incapacitated crew member. They're very few. And then we took that and developed the scenario. So we developed an evidence base for what we actually thought we would actually see in the moon, and weeded out all the weird stuff. The LEV, okay, we impacted that. Again, the thing with the LEV in particular, a couple of years ago when I was at ISIS, which is an excellent conference, the International Conference on Engineering Sciences. It's great for a doc to go to this engineering meeting. You know, I heard a fellow talk about the egress system on the vehicle, where they would reach overhead and pull themselves out, and it was very interesting that they would do that. And I thought, from a clinical standpoint, especially for older shoulders, reaching overhead is one of the worst things you can do. Repetitively loading. Now everyone says, well, in 1.6G it's going to be a big deal. For those of you involved in astronaut training, you train hundreds of hours in 1G before you get there. For those of you who don't know, in the NBL we've injured 12 shoulders requiring rotator cuff repair because of training. So this is an issue. So we went back to look and see what is the best configuration to get out of the suit in the LEV. And actually Jeff and I and one of my grad students, Joe Novak, did this study to look at the different configurations, and really based on, not necessarily based on the evidence we found here because there's some technical problems, but we basically came up with the idea that you really need to have an egress handhold that's more or less here, using the strong pectoral muscles and not loading the shoulder above 90 degrees abduction. That's the way you really should design the vehicle, which was very interesting. And this is actually, it's probably not going to work, won't work, but this is actually something that Grant Schaffner did using Life Mod, where he was actually to videotape and use all the loads and actually showed what the torques were at all the different joints here. Really cool stuff to prove our point. So verification, we use analogs a lot. We're getting close to the end here. Jeff and I, along with Chris Gurdy, a couple other folks a couple of years ago, helped put together this matrix here, looking at all the different analogs that we have available, and then figuring out how, basically we want to be able to take a project or requirement verification or something and find the best environment to put in, because some of them are very remote and very expensive, other ones are very nearby, certainly like our rock pile, or certainly like NEEM or something like that. You know, what's the best environment to actually test your widget or your device or whatever and minimize costs? And that was the big thing. Analog testing is expensive testing, but this gets in the whole idea about subsystem testing versus system integration testing. And I've actually got a paper I'll talk about at the very end. Very interesting idea as far as cost savings and how this impacts the program as a whole. Certainly us in SA, SF, SK, SD are very strapped on what we can spend in research. This is very important to go across. So anyway, Apollo was all about analog testing. As you probably know, Apollo did all kinds of analog testing, and their attitude was, and their recommendation was, make sure you train in as like an environment that you're going to actually be in on Earth, or on the moon or whatever, on Earth, to make sure that you're ramped up, ready to go. Because if something happens, you're going to be best prepared for it. That was their attitude. That's why they did training in New Mexico. They went to Hawaii, lava fields. You all remember the flying bedstead. They did all kinds of stuff to get them ready to be able to do their mission. They trained, they tested stuff, they tried breaking stuff to get there, and you had to be in as mission-like environment as possible. So we took that, and again, we've got the rock pile, we've got Desert Rats, which is very local. Then we've got our very remote places. Again, Haunting Mars up by the North Pole, Nemo, which I've been down to, which is a blast, Antarctica, of course our Zero and Partial G, all that stuff key to doing this kind of work, testing our stuff. So as far as our analog environments, again, one of the things about Haunting Mars I think was real impressive was the fact that we went up there within a concept. We didn't have a lot of technology we were testing, it was more or less a concept. What happened, or how are we going to conduct a situation where a crew member is incapacitated in a crater, slope terrain, they're going to have to get out, and how would we do that with the very limited stuff that we're actually going to have on the moon? We had no idea how to actually do this, and this is where Dr. Chappell came in, because he's a Rocky Mountain rescue expert. Actually, that's what he did, as well as a biomedical engineer before he came here to work for Mike Gernhardt. So we went up to Haunting Mars. For those of you who are aware of it, the crater's out here. It's as similar to the Shackleton crater in the South Pole of the Moon as you can get on Earth. And it's pristine. It's up at the North Pole, so not a lot of people are there. There's some polar bears and some other stuff, but not a lot of other stuff like that. So it's a very, very good environment, but it's kind of far away. It's 4,200 miles away. We did this scenario where we actually had Pascal Lee get incapacitated in the crater, and then I was the other crew member had to go down in the crater, and then using this device that we had designed, actually try to get him up the crater. The interesting thing is, and this is something that Steve had actually designed while he was at the University of Colorado, was this way, one of the ways, many ways, you could actually use very few people to actually get someone out of a crater. We did this. Here's Steve with the winch design that we actually used to be able to carry them out. This is just an example of some of the testing we did beforehand to be able to get them out of the crater. It was very difficult to do, and one thing, we were able to do it. It took probably, what, about 25, 30 minutes to do it, Steve?
Probably less than that, but it was...
It seemed like a long time, but the point was, afterwards, Steve had said that this kind of technique up in Colorado or anything else had really not been done with less than 10 people. Whoa. Well, we're not going to have 10 people on the moon. We're going to have 4, but certainly just 2. We were able to do it. We proved the concept that we actually could do this with very little capability. Fantastic. Sure, you could have done the rock pile, you could have done everything, but some of the other real blessings that came in this was just from a behavioral health standpoint. The team had worked 5 days, about 20 hours, 18, 20 hours a day. Again, 24 hours of daylight, you don't get tired up there, I swear. You do not get tired.
10 milligrams of Ambien at 3 in the morning, 5 o'clock, I was wide awake, and I did that for 9 days straight. Incredible, very mission-like. But the night that we were supposed to get ready, at about midnight, we did a review of the team, and I asked the team, okay, where are we at with our computer connections? Where are we at with all the hardware stuff? And everything was broke. At midnight, the sim was going to start around the world at 6 in the morning. At midnight, everything was broke. The wireless systems, we were talking about the wired systems, nothing was working. And you know, I got a little slap happy, and Gene Kranz says, you know, failure's not an option, guys. We've got to actually do this thing. So the team worked through the entire night, and at 6 o'clock, when France and Montreal and Houston came online, everything worked. That's mission-like. You know, if we had been local, I would argue, and I think I'm right, it would have been very easy to just say, let's close shop, come back fresh in the morning, do it. You can't do that in space. This is what the mission's like. And we proved we could actually do this. So I think from a BHP standpoint, dealing with fatigue, dealing with smelling like stink, et cetera, being hungry, that we actually did this. And, you know, I would argue that you can't do that unless you're really pressed and far away. Anyway, and that was just the team doing all this other stuff. It's really neat up there at the North Pole. You get all these icebergs and stuff, and you get a little slap happy. I jumped in the Arctic Ocean. It's cold. But I'm an Army guy, and I had to set a precedent for all my colleagues. Let's see. What's that?
You're crazy.
You know. This is what we broadcast around the world. We did ultrasound, we did all this stuff, so we tested a lot of our capabilities, medical capabilities, did this stuff. A lot of fun. We were able to show ultrasound. Of course, I can't show you the video because it's not working. Lots of benefits, but this ties in, and I think this is my second to last slide, ties in something that I came across in a paper by Harry Jones from a couple of years ago. He presented this at ISIS about integrated system testing of spacecraft. One of the biggest criticisms we came under when we went and presented this, or present NEMO, or any of these analog testing, is that system level integration testing is too expensive. You have to do subsystem testing. Because if you test your little widgets and get all your widgets working perfectly, then you can bring them together at the very end and you're good to go. Well, here we actually developed some mathematical formulas and looked at that and said, in the end, actually, subsystem testing costs far more than system integration testing. In other words, if you just take your concept, if you take all your stuff, put it together, test it, in the end, you find all your problems out up front, and then you work those out. Whereas if you put all your stuff together, when you get to system, when you do your subsystem testing, when you finally get to showtime, all these problems occur, but the hardware's already been cut, so you got to go back and rework this. Very interesting paper, and I take that because we do a lot of this work. All of us together do a lot of this kind of work, and that was very important. At least let management know that system integration at the system level probably maybe even though up front the costs are more, over the course of developing your spacecraft or whatever, they probably actually save money. And I think certainly from what we learned from Haunt and Mars, getting lessons learned up front and telling us the things that we don't even know about is probably more cost effective than doing all that, getting to that point, and then realizing that you got to do all these other things. So anyway, I just throw that in there because I thought that was very important. So with that, I go back to all this. I'm pretty sure I stuck to all the stuff that I need to do. So at least you get an idea what space medicine's about. It's about a lot more. Again, we do patient care for all the astronauts' lives. There's a lot of other stuff going on. But from an exploration, from a constellation standpoint, you understand how we integrate our ops into our research, how we develop our requirements, how we design this thing, verify it, and that's it. So questions?
Before we start on the questions, just a couple of things. Well, let me just stand close to you so everybody can hear me, because if we have questions, you're going to have the microphone.
Oh, okay.
Our broadcast will end pretty soon, but we have the room for a little bit longer while all of the video equipment is taken down, and so we will keep the room open and have a question and answer session, and apologize to those folks who won't be seeing this live. But I did want to say, first of all, thanks to Dr. Shearing for coming in. That was a very, very good presentation, I think, and a very good representative example of the importance of this integration work. And he is right that if you look at it from an overall perspective, the humans are part of the entire system. They're not just along for the ride, whether it be something they're doing as part of the mission on the ground, or you know, part of the operating the vehicle to get there and back, or keeping themselves sane and healthy while they're waiting to be rescued. The crew's not just along for the ride, their performance enables the mission. So looking at protecting their health and protecting the way that they can perform. It's not just pampering the people, it's protecting the mission, which the people are all part of. And there was some very good, I thought, tie-ins to show you that looking at space medicine, I mean, Dr. Shearing talked about many of the other domains, and when he went through this, talked about environment, you know, lunar dust, habitation, looking at personnel. When we think of the crew, you know, we think of them not only as protecting them from a health standpoint and the performance, the program or project as a whole is looking at the crew as an asset as well. So you don't want to use up your assets, even if you want to look at it in a very cold-hearted manner, so that they're not there for the next mission, so that all of your experienced folks who flew early missions now can't fly in a long-term lunar outpost mission because they've gotten too much radiation, or they've injured themselves getting in and out of the hatch, or injured themselves upon landing. So all of these things are very, very relevant. And also the crew and how the crew integrates with the vehicle does really, really drive the vehicle design. Like you were saying, not only the hatch, but consumables, looking at oxygen and how much you and water and how much you have to bring with you from the very start. And because we work in a very resource limited environment, the program or project manager has to look at, do I add a food warmer? Do I add more propulsion? And it all is, that depends. It depends on the mission. It depends on how long it is. It depends on what you expect the crew to do and what the trade-offs are. But if you don't look at things from an HSI or human-centric point of view, it's hard to trade a person in human health and performance when you do those vehicle trades. And then one more thing, we'll open up to some questions. Just a tease for the next HSI Knowledge broadcast, we're going to be talking a little bit more about that integrated medical model that Dr. Shearing referred to, where you really are looking at, based on risk assessment, what is your level of care that you really, really need to provide in whatever environment you're going to be in. So that's going to be our next one. It's going to be May 14th, I believe. So, yeah. If there are any questions,
please. Certainly, you know, those who are actually watching this, don't hesitate to email me. You know where I'm at, global, and I love to talk about this stuff. So be sure to ask questions. No questions. Everyone's hungry. They want to get out of here. Oh, go ahead, Lauren.
When you did your pull the people out of the ditch exercise, you did that in 1G.
Right.
But presumably it would be somewhat easier
Great question.
on the moon. And how did you decide? Was it sort of a let's be conservative? If we can do it in 1G, we can definitely do it on the moon.
I almost feel like this is a plant because
Well,
I'm gonna bring a point that we learned from Apollo that I hadn't really considered. They said a fatal mistake is to assume that you would be able to do something on the moon in 1.6G and not really demonstrate that you've done in 1G. We took the standpoint, let's demonstrate we can do it in 1G, and then we know it'll just be easier. So we didn't make any modifications. We just worked what was a very, very difficult procedure in 1G, made sure we could do it in 1G, then we knew it would be a lot easier to do in 1.6G. So that's the standpoint we took. Coming from Apollo, Apollo said, make sure you can do everything you need to do in 1G. Don't just try to modify and play around and say, well, it'll be 1.6G, and either don't do it or, you know, do mods. Just do it. Now there may be some, I'm sure there's all kinds of permutations of engineering things that you'd actually do to show what it would be like in 1.6G. But I think from our standpoint, from an operational standpoint, let's just do it, show we can do it, and then, you know, I mean, that night I had such bad back pain, I actually stuck myself with 60 at Toradol on my butt, realizing that if I was on the moon, I probably wouldn't have that back pain because I wouldn't have been lifting the 300-something pounds of Pascal's carcass up that 20-degree slope. But great point, so I'm glad you asked that. So make sure, again, we learned from Apollo, demonstrate what you think you're going to do on the moon or Mars in 1G, make sure you can do it, and then you'll get the bigger bang for your buck in the reduced gravity environment. Great question. What else? A lot of new faces. I don't know if you guys want to see the Apollo thing. You know, that's something that we've done, I think, 42 times now. the different groups. But that was the whole point, to do a road show to make sure everyone learned. Certainly more than willing, whether it's SF, whatever, to give that brief again so you can learn about what we learned, or just get the big 400-page book that we published. You can get that too to make sure that the next generation is at least knows what we know. One of the hardest things around NASA I found is finding all the data. And at least this is one place where all the data is in one spot. It's right here. Killed a lot of trees, but bam, you don't have to go hunting around for what we learned about Apollo. Good. Any other questions? Well, thanks again. This is good. I'm glad you did this, Deb and Kate. Thanks.
Thank you very much.